Good evening, everybody. A fun little combinatorics problem. We're counting the number of ordered pair positive integers. You may have seen this as z plus, but we're just the natural number z plus. We're not including 0. Okay, so 1, 2, 3, 4 ad infinitum. Now we're looking for the number of ordered pairs from the Cartesian product of the positive integers. And so in this kind of an obscure term, I guess, what is a Sphenic integer? Well, Sphenic comes, I don't even know the etymology of the word, but it means that n is the product of exactly 3 distinct primes. R, S, and T are distinct primes, okay? And so it's very clear that the only possible divisor pairs are just 1 times the number itself, and then you break it up into these 3 other combinations, okay? And again, if y'all aren't quite familiar with that, well, there's understood exponents of 1 right here, and you can just work through it directly, or you can just trust that you increment each of these 1s, and that gives you 8. And that's a very well-known result, easy to establish in a number theory course. But that means if you have 8 total divisors, you have 4 divisor pairs, okay? And these are, I've just listed the 4 divisor pairs. Now the idea here is to do some algebra on the equation. It's called completing the product. Some people call it Simon's favorite factoring trick, SFFT. It's a popular technique in, I think, competition mathematics. But what we do right here is kind of a fun little trick here. All I've done is rewritten the left-hand side of our given equation right down here, okay? And notice that the first thing I did was just factor an x out of these 2 terms. So it leaves this. And then what happens right here is a lot of math is just about adding 0. It's kind of almost insulting, but this is just equal to 0. But that gives us a way to get this to this factorization, okay? And again, I hope to make them, let's see, what do we have? X times y plus 1. So we take this y plus 1, and there would be an understood 1 in front of this y plus 1 right here, right? And then this minus 1 would cancel with this plus 1 over here just to leave in, if that makes any sense. Again, folks, we have a common binomial factor of y plus 1 is the reason why we did this. Common binomial factor. So what we get is this, and then we set this equal to 0 to get this result right here. Now, so let's just go through the possibilities. If you put 1 here for this factor, and then n right here corresponding to this, this would make y equals 0. So we can't deal with that. Okay, I mean, y equals 0 is not a solution. It is an integer solution, but it's not a positive integer solution, right? If we put 1, and similarly right here, you would get x equal to 0 if you just called this side of it 1, all right? So we have to exclude this part right here. Okay, we have to exclude this piece right here. Okay, now the rest of the possibilities, what I'm going to do is just write it. I'll just write it down directly here. You have R is a possibility, ST, and again, what I mean by that is you're just equating it to the, in this case, ST would be equal to x plus 1. That would tell you that that x has to be ST minus 1, right? All right, and so you got the RST. What's the other combination? SRT. Remember, we're just trying to count the solutions. So, and then also we have TRS. Like that, okay? Now, and also, this is just, oh, so this one doesn't count, right? This one does not count because of the fact we get 0 for a solution. Okay, we're not interested in the zeros, all right? But this does count, so this would correspond to, right here, this one just would be y is equal to r minus 1. Okay, and ST is equal to, x, ST, if we equate x plus 1 with ST, we get x equals to, that's what I mean, we would get x equals to ST minus 1, right? And again, it's just straightforward. If you stick this right here, you can see that you get what you're looking for, right? ST minus 1, the ones go away, and you have ST. And similar all the way down, folks. And also we can reverse each of these, right? But all of these are reversible, right? Just because of the, I guess, the symmetry. You can reverse each of these, right? Let me go all the way down. And we'll work a concrete example here. So I'm not going to write all that down, but we can write all of it. So you see what we have right here. This is 3 solutions. This corresponds to 3 solutions, but you can reverse all of these assignments. So what we have is 6 solutions. Okay? 6 solutions is the answer to the question. And again, we're talking about ordered positive integer pairs. Okay? So 6 solutions is the answer to the question. Now let's work with just a concrete example. What if we had the equation, what is the smallest sphenic number? It would be 2 times 3 times 7, right? That's the smallest set of distinct primes that multiplied together are 2 times 3 times 7, right? So we would have 2 times 3 times 7. Let's just write down the equation here. X, I'm just trying to remember it here. So if n were equal to 2 times 3 times 7, that would make this 29, right? Okay, that would make this part right here. So let's go down here. So if we have x plus y plus xy, and I think we're going to need minus 29 here. Okay, I'm just going to try to create a solution here so you trust all this. And let me go back. That is the equation we're dealing with, right? Yeah, let's see. Right. Now, why did I pick 29? Because it is an n minus 1 statement, right? But n is equal to 2 times 3 times 5. Okay. Which is equal to 30, right? Okay, now let's just take a look at one of the possibilities. I guess we could do r equals to 2, all right? So we could do r equals 2, and then st would be 15, right? Okay, so a solution to this would be, we can do it either way. I'll just go x is equal to 2 minus 1. Okay. And y would be equal to 3 times 5 minus 1. Y would be equal to 15 minus 1, right? Okay. So this is equal to 1. And this is equal to 14, right? So let's check it out and see if I accidentally got this right. Okay, so right here, if x is 1, so you would get 1 plus 4 is 15. Oh, wow, look at that. And then plus 1 times 14. Plus 14. I'll just write it down, hopefully. Minus 29. So that is a solution, right? That does equal to 0. And you could find 5 others in the fashion that I described, hopefully, up there. So you see, there's one solution right there to this particular one where this is sphenic, right? The product of 3 distinct primes. In fact, this would be the smallest sphenic integer, okay? So this is a check that maybe I know what I'm talking about here. But the overall solution we're looking for in the more general case, how many x, y, the answer to that I'm getting is 6. All right, that is all. Thank you for viewing.